My lecture on PCB design. So there's a bunch of these out there. Why am I uploading one now in 2025 after people have been doing this for years? I gave this recently at Dalhousie University, where I'm an assistant professor, so I put in a lecture on PCB design into one of my classes, and I've made the slides available on GitHub. So I thought I'd record this in case it's useful for anyone. There is some other great resources. I've tried to link to as many as I know about, but it's something that I had to record for my class anyway, so I thought it might be an interesting thing to include on my channel. I'm recording it as is, so there's a warning that there's way too much, even this part. So what's going to happen is it's split into 4 parts. The first part here is going to be on generics of PCBs, and on the design process and considerations around the design. The second part is going to be about how you actually order them. So we're then going to look at, assuming you have a PCB, how would you order that? The third part is actually designing it with KiCad, so the actual hands-on part, which is really the best way to learn. So I will also give you the caveat that the lecture is kind of suited for, it was designed to be in a university where you can't have the nice interaction between let's do a bunch of stuff hands-on. You kind of lecture, and then there's lab sessions and projects. If you're doing this, I would really encourage you to, fire up KiCad at the same time, if you feel like you need that hands-on learning. But the way the lecture is structured, it's not till part 3 we'll look at the intro to KiCad, and then part 4 is once you get the boards back, how do you actually bring it up? There is a part 5 kind of. So the part 5 is there's a group project or a project with the university group where they're making a controller for an inductive load like a motor or electromagnet or something. So there's actually going to be a project that's designed for those students, but it goes over a little more about using KiCad and some specifics of parts beyond what I'm going to cover here. So you may also want to check out for that once it's posted, which should be very shortly. It may even be alongside this video. I'm not sure on the timing. But yeah, so if you want to stick with me, let's get to it. So background here. So I've designed over the years a lot of boards. This is very vague, few hundred designs. A lot are open source, just simple little 2-layer boards. Design something I need for a little possibly a test. I've got lots of boards that were used for just testing an idea, right? Once you start doing this stuff, it's pretty easy to spin new boards up. Some are more complex, some use layers, more complex parts, bigger parts, smaller parts, things like that. So, normally 2 to 12 layers. I haven't done a lot of cost optimized. Like when you start looking at consumer electronics or really high volume products or really low cost products, and you start to say, okay, well, we want to spend a lot of time to cost optimize this. Normally it's not an issue for prototypes, so hopefully that doesn't matter anyway. But I also give you the caveat that if you're looking to do cost optimized, there is a lot more work that you have to do there. But when you're doing this, a lot of the time, if you're in a professional environment, the highest cost thing is the engineering time. So also think about that. It often makes sense to use more layers just to save a bit of engineering time because the engineering time is a lot more expensive. Here's some PCBs, right? So over the years, so more recent ones related to Open Titan project, lots of stuff with new AE technology like Chip Whisperer Husky, Chip Whisperer Lite, Pico EMP, some of these projects you've probably seen, but there's lots of internal stuff I've done as well over the years. But why do we have PCBs? So if we start at the beginning of, electronics, not beginning of electronics, but sort of consumer electronics mass produced, right? You'll see stuff where you sort of have like here's, tube or switch or some sort of connection where you have a bunch of parts like resistors, just soldered, right, point to point. There's no, we don't have the printed circuit board that this is all built on. We just have stuff that might be strapped down, might be floating, things like that, but it's all soldered together. There's wires where it's needed to connect parts and other things between the devices. So this is kind of the beginning of, mass-produced electronics are built in this way. The next step beyond that is, there's many steps, but we have boards like this where we kind of have like a board with the parts on it, but there's not really traces interconnecting them. What they do have though is, there's an isolated board and there's pegs, and there's wires that are wrapped around them. So there's actually quite complex boards can be made with this wire wrapping. You can make good prototypes with it. I've made bunch over the years of this type, and so you can do a lot of pretty complex boards with wire wrapping sort of techniques. So this is the precursor to now what we want to get, which is a printed circuit board. A printed circuit board has a core, which is normally some sort of fiberglass material, and then there's copper traces on top of it. So these copper traces are the interesting part to us because that's what the signals run on. This is how the board itself functions. You'll notice there's no connection in this very basic one. We just have insulated core with copper traces and no connection between the top and bottom. So that's going to be the next step over, where we plate the top and bottom layers together. But for now, we ignore that. And the reason I start with this is because this is actually how you can make boards, back in the day, but still today you can make it. So if you were making them a while ago, you might have gone to Radio Shack and they would sell you a little etching kit, which had like a fish tank heater and a little pump that would bubble up. So you'd have your ferrochloric acid in this, and to make a PCB, you'd get a blank piece of, it had the core with copper on both sides, and you'd either transfer onto your design, or as in this video I linked here, you could draw it on with a Sharpie, and then you put this in the tank, and the tank etches away everything that wasn't coated. So everything where you want to leave a trace, you draw on it, or use a toner transfer, or whatever it is, and then it etches away the copper you want gone. That copper kind of goes into a solution here, and you pull the board out, and you've got a circuit board. So you have to drill holes and stuff like that still too to get a board that looks more like what you're used to, but that's the basic idea of it. You can do this now with a milling machine, so this is still pretty common, especially for like RF and things where you might want to test a lot of different ideas really quickly. You can use a milling machine to make boards, and what you can see is that it's basically milling away. It doesn't mill away all the copper we don't want, but it just creates an isolated path. So here's a board I made with a surface mount part on it, right? And this is actually a chip whisperer target board, but you can see there's kind of these paths around it that are isolating traces from copper. And you kind of have some dead copper. So one of the things with milled boards is you end up with this sort of dead copper here that's just not connected to anything. You wouldn't normally have that with a circuit board. You'd either have that as a ground or just fully remove it. The reason I kind of mentioned this is that you may have a milling machine in, for example, a makerspace. Maybe you have one yourself that you like a Carvera, you use them for something else, and you said, hey, you know what, I can make PCBs now, let's get into PCB design. Great. Just consider how you plan on making your board, because there's going to be different choices you make about, like this board doesn't have any plated through holes. It basically, we need to put a lead in here and solder it to make an electrical connection. So when we design the board, we probably want to reduce how many holes we have that we've got to do that for. Similarly, there's, we need more space than if we got a board made commercially. So you want to think about that and make sure you're matching your design specs with how you plan on getting the board made. It's going to make your life way easier if you do that ahead of time. So as I kind of mentioned, the general, what we'll normally consider a PCB has the copper on both sides plus plated through holes process. So the plated through holes will plate from the top to the bottom. We also will normally plate over the copper itself. So copper will oxidize. So we don't like raw copper. We like a coating on it. There's a few different finishes, we'll call them, that we'll typically find on copper we'll talk about, but the first step is this plating process, which will plate through these holes, and depending on how we're doing this, may plate other sections of the board as well. I should note that you can actually if you're doing a milled board, there is ways to get this, so you can get little rivets you can put in. You can get your own plating process to plate over tin, so there is ways to do it, but generally, if you're making your own DIY PCBs, often you don't bother with that stuff. You're just milling it for a quick test, and you leave the plated through hole to avoid your order. But you don't have to. What you'll then do is add something called, or what the manufacturer will do, is something called solder mask. So solder mask is the characteristic, if you look at the PCB, you know, and it looks green, that green color is actually the solder mask that's on the PCB. And so the solder mask goes everywhere that we do not want exposed connections, aka where we don't want to solder. So hence the name solder mask. We're masking away all the stuff that we don't want solder to get on and we don't want to accidentally short out. Here's a close-up view of a circuit board where we have pads in the middle here. The solder mask in this case is black and is basically just everywhere that's over the rest of the board. There's a tiny gap around the pads because we can't be perfectly aligned, and this is where we kind of have, so what's actually happened here is all of this is missing solder mask and the pads have been exposed. You can probably see just at the edge here, right, when it starts to go into the trace, we can start to see the beginning of the trace here. And it looks silvery because this board's coated with something called hotter surface level finish, so it's like a solder finish that's then smoothed over. So I've got a black board similar to what you saw on the slides, and again, there's the solder mask is this black stuff. This here is a hotter surface level finish on the exposed, what would be the exposed copper. So with this finish, everywhere, if I peel back this mask, like if I were to scratch it here, I don't know if I'll be able to scratch it with this, but you'll actually see, okay, there you go, right? You can see the copper below. So there's no plating here, it's just straight copper, because then over top of the copper would be the hot air surface level solder finish, and there's the mask on top of it. So, you know, you can see if I peel back the copper, I get the, or peel back the solder mask, sorry, I get the copper. Here's another board, this is green, right? And so this one you can see, it's pretty tight to see. There's kind of some gray around the pad, so that's where we have the mask missing. And here's another board with a red solder mask, right? So again, you have different colors. You can get all sorts of colors, and that is your solder mask. Silkscreen is the other thing. So the silkscreen is, and let's go back to the camera here, the white, typically white, but it again can be other colors, and it's used for identifying parts on the board, and you know, normally it's used for assembly purposes, so you can say where, you know, what capacitors are where and things like that. This was an early prototype board, and so I was pretty lazy with the design, and we'll talk about cleaning up the design later. And I say that because if you notice here, a bunch of these are cut off. Like this should say R39, but it doesn't. It just says R39. The R40 is cut off there because the silkscreen gets cut away from the solder mask openings, right? Because that would be bad if it went over. So the PCB fabs will almost always do this for you. They will not let, it'll be an error, but they'll most of the time cut it back for you. Right, see this U6 is not affected, but a lot of things I just let them kind of be as they were. But you can see the solder mask does not go over the pads. And how the solder mask is applied, by the way, can vary. You'll see different appearances. So sometimes there's like a digital, so this looks like a digital printing. You can sort of see the pixelated section here. So you can see this sort of pixelated from the digital printing. Sometimes it is like a, you know, silkscreen process, like there's a actual sort of template, whatever you would call that, that you push over with the classic sort of silkscreen process. So it can vary, the quality can vary. This is all stuff when we go to order. There's different options you often have. But okay, there's your solder mask. The finish, I already mentioned briefly that we had this hot air surface level finish. And where this becomes really obvious is if I take a board and I put it on an angle here, this part of the board is for what's called a ball grid array, which is a part that has a lot of balls on the bottom side. It's a denser part. It has to lay really flat. and I actually want my board surface to be very flat. So there's a spec on how flat it should be for the part to solder reliably. You'll see with this hot air surface level, there's, some of these actually stick up noticeably, right? So what's happened is that the way this works is there's solder everywhere on the board. A hot air knife basically is used to level it out. And, because where the solder mask is, it won't stick. And so it'll flow away. But it's not perfect, right? So depending on just whatever random variations, we get some small changes in the size of the, the amount of solder deposited. So we actually have variations in that finish, which isn't great for soldering certain devices. So in that case, I would prefer an electroless nickel immersion gold, or ENIG finish. This ENIG finish, as you can see, it looks super flat, and you don't see any of that variation because it's all plated, chemically plated on, or electroplated, I guess, not just chemically. And so this plating it gives you that shiny gold finish. And so this is a much higher quality finish. The cost isn't that much more, so often I'll use an ENIG finish just because. But sometimes prototype can be helpful because, here you see you actually have tiny bits of solder on your board already. So that can be a tiny bit helpful for certain prototyping techniques I will mention. And we'll talk about that in part 4 when we go to assembly. Yeah, so those are the two finishes. If you do get harder surface level finish, match your solder type. So I always use lead-free solder. I recommend everyone does it. If you've always used lead-free, you never have concerns about contamination of a lead-free process. You never have concerns about, was there a possibility that lead leached into something because you don't have lead in your process. So I'm using lead-free hot air surface level finish, or ENIG as my common ordering finishes. With our PCB, so that was the top and bottom layer, right, when we talked about this. We can have more internal layers, and so internal layers are inside that layer. How this is made, it actually varies how it can be made. So this is one way of making it. More commonly, we have this system where you can see it's basically like two boards, right, two-layer boards, that get stuck together with a pre-preg, this in-between board. So what you do is, or what the manufacturer does, is they're etching two layers of your board, which are like two half-width boards, and then they sandwich them together with material in the middle. So multi-layer lamination is done by etching pairs of them. So you always end up with boards, or almost always, I should say, I guess, but most of the time, you go from 2 layers to 4 layers to 6 layers to 8 layers. So when you're designing a board, if you think, I just need 1 more layer, it doesn't matter. You have to go to 2 more layers. It would be much more expensive to try to get a 5-layer board than a 6-layer board. So the reason we want multiple layers, and we'll talk about this later, is that we can do stuff like just have, hey, this is all ground. So, in your circuit, you probably have lots of things connecting to ground. Now you can just, from here, add a via, and the via goes through everything, to ground. And you don't have to worry about routing, okay, how many places do I have to get ground to? Same thing for power, right? I can just say, power goes to 100 different parts. Now I have a plane that does it all. There's some other advantages that we'll look at later that would also give us reasons we want to do this. When we talk about PCBs, note that a PCB A is an assembly. So this basically means you've got all your parts on your PCB. It used to be, that to get a board assembled was not a ton of effort, but more effort, more cost. You wouldn't do it as a one-off. That's changed recently. There's been some places that have always done small-scale assembly, but now like JLPCB and other fabs will do it, but JLPCB currently has a really nice interface that makes it super easy. Even if you're only building a few boards up, sometimes it's more efficient to get them built for you. If you're not used to soldering surface mount parts assembly, you may like this because when you're doing a bring up of a new board, right, you're prototyping your design and your assembly. If you had firmware, your firmware as well. So what you might like is that you don't have to think about have I done the design correctly? You might prefer that someone else has done the assembly for you and presumably that soldering has been done to a higher quality than you're going to do. Okay, so we talked about PCBs, we talked about sort of the generic stack up. If we look at a board, we've got some other parts here. So let me do this. Let me pull up my live board because we got, don't have to use just slides here. Okay, so I'll use the red board right here. Right, so let's go find somewhere interesting. So these parts here we call the pads, right? So these are pads of my component. They get soldered onto, or the component gets soldered onto these pads. So each of these is a pad. We have the traces, which are the copper that's actually carrying signals and power and things like that. Our via, which we've already brought up, are something that connects between, you know, this top side to the bottom side. And the via itself, which is a combination of like a pad and this drill in the middle, you know, is a combination of this outer pad, the drill that goes through the pad to the other side, and then the fact that it's all plated together. So when we spec a design, we'll have some different things that we need to tell the manufacturer about what we want the design, you know, parameters to be, the size of that hole, stuff like that. So let's brief note about the software. So KiCad is what I'm going to use in part 3 here. It's free, so this is great for a YouTube video. You might wonder, well, professionally, is that still the case? I should tell, or, you know, give you the background that I've used Eagle for many years before it was acquired by Autodesk. At some point when I was doing designs, I effectively really needed more capabilities than Eagle had, so I had moved to Altium Designer, which is a pretty expensive professional design tool. It's been around for a while, so I've been using it for like 8 years now. At the time I was switched to Altium Designer, KiCad was missing a lot of pretty key features, including like push and shove routing and things like that have since been added. We, as part of New Age Technology, actually are switching to KiCad because we see that the, you know, current state of it is more than sufficient for our designs. We actually have an old Altium Designer permanent license, but if you were to get Altium Designer now, you can't buy a license. You have to pay yearly for it, which means that if you need to keep a design around, you would need to continue paying, right? So even if you have one design that you're like, we might need to change something, you can't just get a permanent license for it. So there's a bit of a risk of long-term kind of lock-in, you know, that it's fine if you are actively developing, but say you switch and you still need it, you're forced to pay long-term. So for a lot of reasons, I really recommend people look carefully at that. And I, you know, despite having only recently switched to KiCad, I've been very happy. KiCad 9 adds a lot of new features, including things like via pad stacks, and these are more advanced things, but that were in Altium Designer, weren't in KiCad until recently. The other thing you might come across is things like ECED, and there's a few of these where they're tied to a PCB fab or a fab. You're not really going to see these professionally because they're just too tied to a fab and your design files are locked up and they're more limited. They are pretty nice in some ways though, like, you know, this one's in your web browser, I believe, and so it's easy to share if you're doing a group project. It's really easy. People don't have to install it and you discover they have the wrong version. It's all just in the cloud. If you're going to be ordering from JLPCB anyway, then you know what, you may actually want to just consider that. Ultimately, whatever you choose, the process is the same. It's not that difficult to switch. Each of them has different ways of doing things, but don't think that you're going to have to pick one and stay with it forever, especially if you're just learning, right? If you're starting a company, you may have some pain in switching in 5 years from now because you have all this legacy. But if you're just learning, you know, and you say, hey, I've, you know, my best friend or my colleague is using ECED, they could teach me a bit, go for it. They're using Altium Designer, go for it. Whatever makes sense for you, I'm going to use KiCad. All right, so this video is extra long because it kind of rolls the intro into part 1 of the PCB design. So the PCB design stuff. The first thing I'm going to tell you is there's a super odd thing with PCB design, this unit of mills. So it's really only used or heavily used in PCB design. I have this big flag up because sometimes it causes problems if you're talking to someone, if you're saying doing a project where someone else is working on an enclosure without any PCB experience. You know, a mill, which we use a ton in PCB design, is equal to basically 1/1000th of an inch, which is often called a thou elsewhere. So 1 mil is 0.001 inches, which is a thou, or 0.0254 millimeters. So it's not, 1 mil is not a millimeter, right? That's the important thing. Sometimes people, you know, confuse those, and obviously this is then going to cause a lot of issues when you're trying to discuss sizes of dimensions of enclosures and things like that. Normally the mill is only used within the PCB, so the first place we'd use it is trace and space, which is really the name given to what is the width of this trace here. The width of this trace is how wide that conductor is that's carrying our signals. The other thing we need to consider is how close can I put that conductor to another signal. Why this comes up is, right, we still etch, like all of this fancy work is still using those etching, like those tanks I showed earlier. And so when you etch, you have copper, right? And what you tend to get is there's kind of some under etch. So if I have my copper on my board, right, the traces, because what happens is this is the resist. So this is the part where I've said, you know, don't allow the etching to get to my copper, but it's going to go around the side a tiny bit. So there's sort of some limits if it gets too narrow, and then it's, you know, you're going to basically etch away the entire trace. And so as we get nearer, the process's controls get tighter. It basically just costs way more money, right? And by that, I mean, if I go to like a trace and space of 4 or 3 mil, which I need for some of the more recent packages, so we do boards at that state, but you know, I'm probably not going to flinch if I spend $1,000 on a prototype board. There are some cheaper boards out there that you could get, but you know, that's, if I'm doing that board, I may end up with that level of cost, and it's probably, you know, what I expect to some degree, right? If I do this, I probably would expect to spend like $2 on a board, which would be a super cheap jail PCB thing. But the point is that, you know, there's a huge variation in the cost. Really, even 5 or 6 mil is pretty common nowadays. So you can get pretty small boards that are going to do almost everything except for very, very small parts on almost any process. The other thing with the width is that what you have is that you're basically making a resistor, right? Remember that, you know, this is a certain amount of copper area that we define by the length, and the thickness is sort of defined by, we can get different weights of the copper, it's called, but it's basically the standard thickness of the copper. So really, the width of that trace is defining how much resistance exists per unit length. Why this matters is, say I took a trace like this guy here, and I had a wider trace and a narrower trace in one line. On this board, I haven't actually had this, so it wasn't designed this way. I just, you know, or it wasn't designed on purpose this way. You use 2 different widths here whenever I did this board. What you effectively have is like a little circuit where you have a bigger resistance and a smaller resistance, right? If you have these 2 resistors in series, and say it was driving a motor or whatever it's driving that's passing, say, 2 amps of current, well, if we pass 2 amps of current, we know that there'd be, you know, 2 times 10 equals 20 volts here, and 2 times 1 equals 2 volts here. So we'd have 2 volts, 20 volts. We could calculate how much power is being dissipated by I times V. So if we had 20 volts across this resistor, like there, this means that the power dissipated, right, is 20 times 2. Remember I said 2 amps. 20 volts equals 40 watts. In this 1 ohm resistor, it would just be 2 volts times 2 amps equals 4 watts, right? So the power dissipation here is much less for the smaller resistor than the bigger resistor, even though they're both in series. So same thing here. This narrower trace is a higher resistance, so it's going to heat up a lot more than the wider trace. And I can test that with a thermal camera passing 2 amps through my board. We can see visually that that narrow trace lights up. It's starting to heat up, and I only leave it on for a few seconds here, but it'll start to get quite hot. Obviously, as you heat up, this is an issue because the PCB is only rated for such a high temperature, so the trace will damage the board. It can start to delaminate, and eventually would burn up if it got hot enough. So that's kind of why we also might need to adjust our widths. The lower limit of trace in space, so don't do your whole board right at I can do a 5 mil trace in space, don't do 5 mil everywhere, because, well, as I just discussed, power and stuff might need more, but it's always good practice to keep the width and the width and the space as high as possible. So for example, on my board where I'm doing that 4 mil trace in space, I have a part called a ball grid array, BGA, where I have very tight breakout, and I'm using 4 mil, I forget if it's 4 or 3 mil, but right, I'm using it in that area to get out. Outside of that, and I basically set a design rule that says use the narrow space, the expensive, super close trace in space in there. Outside of that, go to a wider trace in space because I got lots of room. I only need it in that one spot. So it's good practice if you can do that to, give the fab the most chance of success. But again, if you're starting out, you probably got lots of room. 10 mil trace in space is a good starting point, 0.25 millimeter. Get your power traces bigger. Doesn't hurt to do that in general, just as it's good practice. The power traces will have lower impedance, so there's reasons beyond just temperature rise. In DAL, there's a project where you're going to calculate the temperature rise of the trace. It's in the slides. But if you want to see this, so here's a link, for example, Proto Express, just one of these online calculators, there's a few of them, will let you calculate what the temperature rise is for a given trace width. So you can see how that actually affects everything. When we're looking at our vias on the board is another thing to consider. The vias have, the connection between top, bottom, and interior layers. It looks like just a hole with a pad around it. And what's important to realize is it's a bit odd. We actually specified the final, what we want this hole size to be, which makes sense, but that's not what gets drilled. Because what actually happens is there's a plating process I mentioned, that's the through-hole plating, right? And so we have the through-hole plating, and that means we have a slightly bigger drill than what we specify. So the actual the drill size is bigger than the final size. And so when we design it, we're always specifying the finished hole size, or almost always. But just watch out for that, because it's, again, something that you have to realize there is a little more space needed. And we need to give the manufacturer a high enough annular ring, so we need the via to have a larger pad than that annular ring to avoid a condition called breakout, which would happen if, our drill is not perfectly central. It'll break out of the pad, which then is going to give us very bad, huge reliability issues here. So we never want the breakout to happen. So there's always for a given drill, they'll normally tell you an annular ring specification, which defines what's the smallest pad size you can use. Okay, so yeah, this is just something, as the annular ring goes down, chances of breakout go up, which makes sense. You may also see something called tenting. So with tenting, we have solder mask just covering the whole vias. There's basically just solder mask everywhere. Sometimes it goes through the hole because you have this hole in the board, right? The liquid solder mask is following through it. Sometimes it kind of gets stuck like that. So why you would want that, or why you would care, is that the tented vias allow you to actually have silkscreen over them. So let me see if I can find a spot here with a via. Right here you can see just the edge of this LED text, right? It's over top of the what would be the via pad, right? If I didn't have that, the manufacturer, if I didn't tent that, the manufacturer would be cutting back my text. So often we want lots of silkscreen text to be unbroken, and so we want tenting. So here you can see, for example, the silkscreen text has actually gone in the hole as well, right? So what would happen though if I wasn't tented, it would be cut back to the exposed copper. So it would be cut back even more. So the tenting, depending on your via drill size, right? Like here, my drill is big enough that basically the solder mask is falling through. Sometimes on this other board here, let's try to find a few. There's some where you can kind of see, hopefully, that the the solder mask is actually giving you a surface. And if I find a via with some text over it, some of these aren't good because I've cut them back. See, these overlap. Okay, there we go. So there's 4 here. Where's my pointer? Right, this 4 here is overlapping with the via. So it's cut off because of the pad. As I said, this was a lazy board. This 8 here, for example, is directly overlapping a via. You'd never know there's a via under there. So you might not want to tent them so that you have nice pads exposed. You can use them as test points. And as we'll discuss in part 4, it's a bit easier to modify the PCB if you do that. Random via sizes. So again, what do you use to start? KiCad defaults are probably fine. I'm something like a 20 mil drill and a 40 mil pad is pretty big. So you could use that as a starting point. And then if you start to feel like this feels like it's getting crazy, you could go down from there, but that's a reasonable starting point. It's going to give you lots of annular ring. You're not going to run into big problems. However, again, caveat, if you were doing this, if you said, I want to make this on my CNC mill, you should go look up what is good recommended drill size would be for that, because you probably want as big a drill size as you possibly can to reduce your bit breakage. For lower cost boards, so 12 mil drill with 24 mil pad, or 0.3 drill, 0.6 millimeter pad is kind of my go-to. So on like the Chip Whisperer Lite, I think that the ones I was showing you there, I think they're, and this is just from memory, are all that size. For a lot of like BGAs now, I'm going down to like 0.2 millimeter drill, right? So that helps with some of the breakout of the BGA and stuff, which is way more advanced topic. We're not even going to touch in this little intro lecture. Watch out for higher power, or if you need thermal relief, it's pretty common to put a few in parallel. If you I'm trying to find, let's see, where is this? I've got a switching regulator in here, right? And so I've got this what is this even? I don't know if this is just a ground path, right? But you can see I've got a bunch of vias. One would be connected, but I want a low impedance source, so I've got a bunch in parallel. Sometimes you'll have that, same thing here, right? I've got 3 vias to this one pad that's going to this inductor here. I think, so these are probably connecting into power planes. But that's pretty common, is that you may use multiple vias. Sometimes you have thermal, so you'll have stuff like a thermal pad where it's got a whole bunch of vias because it's trying to connect the heat through the vias to the other side of the board where you might have more surface area. So as I said, always check that your defaults make sense. It's so much more annoying. If I have to go, like this board here, tons of room in the board. What if I realized, oh shoot, these two, I've got to make them like this big? Well, now I've got to go through and move each via out. Even though I had the room to start with, I've got to go back and move everything if I have to change them. The other thing that you can do is via and pad. So this is really easy mistake to make. What you might think is like, oh great, I'll just put a via right here. It's right, super low impedance, looks great, rather than having this little bit of circuit board here. The problem with this is that your via is also in the area you're soldering. So here, you solder here, and there's solder mask, and your via, whether it's tented or not, there's a bridge, and solder's not going to go down your via. With a via and pad, that solder is going to wick down into your via and create a poor joint. You of course have the via top open because you can't tent it. So if you do via and pad, it costs more money because they're going to do this process. They're going to cap the via by filling it with some sort of epoxy and then cap it to give it a flat surface for the part to go on. So this is a lot more expensive. With the caveat that it's like everything, it gets cheaper. So if you do a higher end board, if you do like 8-layer boards, often they seem to be throwing this in for free or by default now, especially if you're going to smaller via sizes. So if you do a 0.2 millimeter board, I think and this, don't quote me on this because, I think it was PCB was just giving you by default capped vias when you did the smaller via sizes anyway. Or maybe it was higher layers, something like that. So it used to be a big thing, but it's always good practice. If you don't need the space, do not do this, right? And it's very easy to do because you might just push the via in a little bit closer, and all of a sudden you're in a via and pad, right? This little bit of thing here is just what you need. So I mentioned that I was going to talk about power planes and things like that. So very briefly, I'm not giving a huge overview of good routing and everything like that, but I will mention this pretty common problem, especially with the 2-layer board, where here what I have is I've got a big ground copper area. What's pretty common is, right, say I had some other traces in here, which meant I have to have this effectively this slot, right? So I have this slot in my ground. And what this is trying to show you is that if I had power flowing here, we like to think that the power follows underneath or wants to follow as close as possible to the outgoing. The return power current, is following as close as possible to the current going out. So that sounds good, except that there's this slot here. So now what has to happen is the return current goes all the way out here and then back. The problem with that is that you have a big loop here. And this loop means you have stronger emissions. And this is, at Dow, there was a EM Fields course they should have taken. And this loop area basically means that you have a larger loop area. If you look at a point far away from a loop area, the magnetic field at this point in time, or at this point in space, not time, is going to depend on the area, aka the radius, as well as the current through it and stuff like that. But as the radius goes up and the area goes up, that field becomes stronger. Oops. Right, and we don't want a stronger field because it's a compliance issue. So here, what I've done is I still have that same limitation that I couldn't route a trace here, but I've routed my outgoing power trace away from that gap. So I'm thinking about where the return current's going to flow and making sure I have a smaller loop area, because the loop area is the area between the outgoing and incoming. So it's a smaller radiated field. It's an issue, as I said, for compliance. So compliance is something that you don't have to think about as a prototype. When you go to commercially do it, that's a whole other topic. So there's a guy, Andy Eddy, who has some really great resources at emcfastpass.com. So he's Canadian. So always support him. And he's got, lots of great resources. This is an example of showing you how, there's this limit here that's basically saying at some distance away, your product can only have emissions below that limit. So you have emissions above this, bad news, you failed. Some of that might be because you did silly things like that. Even without compliance though, right, those emissions could cause like your microcontroller to reset. Say this was your motor controller and you had a microcontroller over here. You may actually get emissions that cause bad things to happen even within your system. So it's always good practice to reduce those loops. Dave Jones has a great video on this. So he, and in particular, I really like it because he took a 4-layer board and a 2-layer board, compared the two of them, and, you can actually see the emissions change. And he'll walk you through, what those look like and also how you're getting, for example, if you look at a trace here, right, you'll have a trace, you'll have a return flow that hopefully, if there's a ground floor, it could possibly follow on that layer. but often, you know, it's got to make it past somewhere where it can no longer, there's an intersecting trace, so it can't get past that. The bottom layer now has all these other traces. There's only the 2 layers, so it's very limited. When you go to 4 layers, what you have is you have ground everywhere, so hopefully the return current most of the time can flow right under the trace. Everything works really well. So these get into way more advanced topics, but it's good to know about it when you're starting out even. Footprint. So when we look at a part has a PCB footprint, and the footprint is these little copper pads that it'll fit on. The footprint is designed to provide reliable soldering, so it's a little bit bigger than the leads on the parts. How much bigger is generally defined by some specs related to reliable soldering. The one thing I will mention is that when you select a part, you sometimes will have a choice. So this is like a TQFP, this is a FPGA. This one you didn't have too much choice, but you had this 0.5 millimeter pitch, which is the diameter between the paths. The bigger the pitch, the easier it's going to be to solder and work with for prototyping, right? So like if I'm looking at something like an AVR, like the Arduino microcontroller, I could actually pick, 0.8 millimeter package. They have a bunch of devices in that package. They do have devices in smaller packages because I might want a smaller package, but that's going to be harder to solder. So take a watch out when you're selecting packages. Think about your assembly. Again, always think about what you're actually going to do here. Don't just pick, let's just pick this random part that's in a crazy small package. That's going to make your life way harder. Most of these packages are designed, or footprints are designed for production soldering. You can do things if you know you're, for example, hand soldering. So here's an example, and there's some of these built into KiCad where you have much bigger pads. So these pads are way bigger than you'd have in a production type thing, but they're designed to make it easier to hand solder. Surface mount parts. So we're going to use a lot of surface mount parts. You might not be as used to them, but once you get used to it, it's super easy to solder. There's really good semi-automated ways to do it. We're going to look at examples later on. So in part 4, we're going to talk about how you do the board assembly and bring up. But it is worth, it's something that a lot of parts are only available in surface mount nowadays. So it's something you're definitely going to have to get familiar with. I will mention one thing that can trip people up with surface mount parts. When you look at little resistors and capacitors, they have this notation for the size. You'll see like 0.805. This is just the 0.8 is literally, it's 0.08 inches in length and 0.05 inches in width. So it comes from that. That's where their sizes come from. Of course, there's a metric version of that because you also have a 2 millimeter and 1.25 millimeters, so 2012. So if you're selecting parts, just make sure you're matching. A lot of the time they have the slash, they'll say both metric and inch, but just don't mess up and accidentally order the wrong type because you'll end up with a part way bigger or smaller than you were planning for. 805 is like a pretty reasonable size to get started with. 1206 is maybe even better. These are pretty big parts. As you get more familiar, 603 is probably the most common size when, space isn't hugely constrained and there's no other major constraints. 402 and below are pretty common for, moderately space constrained stuff. So a cell phone is going to use even smaller parts, but if you're designing like a kind of standard circuit board, 603 and 402 are, the most common, I'd say. Part of that is that when you go for the assembly, if you look at, for example, what JL PCB's assembly services will offer, as you get to smaller parts, it gets more expensive. So there's a lot of reasons that you don't want to just use the smallest part you can. Also, power handling and a lot of things go down with smaller sizes. There's very, very little downside to too big a package. So if you select a 1206 or 805 part, there's very, you're not going to run into like, oh shoot, the power, it can't handle the power dissipation. You're more likely to run into that with 402 or something like that. So when you're looking, again, I recommend just sticking with some of those larger sizes until you get a better feel for PCB assembly. It's always a good idea to check footprints, right, against the datasheet. And when you get them, or when you get a board designed, if you have time, I like to print it out and get the parts in and make sure that at least some of the key ones are going to fit, so I didn't mess up the footprint. I didn't like, oh no, the pitch is wrong, things like that. So it's always a good idea. The solder mask, we mentioned about the solder mask. One thing I didn't talk about is that you also have this case where you can have solder mask between the pins, and this is good because it's preventing solder from bridging. But there's a minimum solder mask width you have. So normally in a lot of footprints you'll see it just removed. So in finer pitch footprints you'll see it removed. And this is because we can't fit a solder mask below some point. This depends on the fab. It's relatively constant, but I bring this up because, occasionally you'll get stuff like a part like this. They actually want to remove the solder mask, and they may just do it. They may tell you, but it's worth knowing about that as well. That there is a point where it makes sense to just remove the solder mask entirely because it's just too fine to fit in your footprint. When it comes to multi-layer boards, we've brought this up a few times without fully explaining it, but we basically have multi-layer boards. Just trying to go back to this stack up here, right? You have like a plane, right? So I have this power plane or ground plane here and this power plane here. And the idea here is that if I have my FPGA on top, or my big part, right, or any part really, it makes it really easy to then just go down to a power plane without having to route a million traces around. And this is going to make life easier. It's going to make our impedance lower. It's going to make our emissions lower. So it's very nice when you can to have these planes and pores. So a plane means I've taken a whole layer for just this signal. A pore means I've poured in an area the copper, that I connected to ground. And sometimes people just do this at the end. They say, let's just pour ground everywhere and maybe put some extra vias to give me a little more ground, anywhere else. On a 2-layer board, it's not a bad idea because it doesn't hurt to have more ground connections for the most part. Here you can see, for example, there's some of these vias, and it's a little hard to see, but some of these vias are connecting to my plane. Most of them there's a bigger black ring around it, are not connected. So some of these are connected, some are not. I bring this picture up because one other thing you can run into if you do a ground plane, if you're doing a 4-layer board, it's not just magic. Think about, if you look here, you'll notice that these vias are not connected to the ground plane, and they actually make a section where the plane could be fully broken. If I'm not careful, I could have extended this I could make like a pretty big break in the plane if I stack my vias up, right? And so this means that if I cross a plane, right, I now get back into this big loop because it would have to go all the way around that. So if you're using a plane, watch out for the vias. If you have the density that's too high, you can actually puncture your plane. So that's something else to watch out for with using them. Okay, so that is the end of part 1. So thanks for hopefully sticking around. What we're going to look at in part 2, which will be a second video, is we're going to assume you have the design so that you can actually go quote it and order it. And the reason we skip the design for now is what I want to show you is how the changes in drills and things like that affects the price. So once you know how to quote the design, you'll know how to navigate the websites to get an idea for what your design specs should be, and then you can feed that back into the design. Take a look out for part 2, which will be the ordering, and we'll then look at the KiCad in part 3 and the assembly in part 4. And finally, part 5, which is sort of the bonus part, you'll look at a little example design, which is this inductive motor driver I mentioned. So you can get a link to the slides if you want in the description, but otherwise, thanks for watching.